Savart law, and the notes are kind of out of order. Let's actually start with the third page on the notes. Okay, so the Biot law says this. It says that a little line segment of length ds carrying current I produces a B field that's equal to mu naught I over 4 pi times ds cross r hat over r squared. Man, that sounds really complicated, but here's what we're talking about. We're talking about Ampere's law is really good for infinitely long wires. It tells us that the B field created is mu naught I over 2 pi r. But what if the wire's not infinitely long? What if it's a wire in a loop or just a straight wire? Well, we can break it down and we can say that a really small segment of wire of length ds does produce, carrying a current I, does produce a little bitty B field dB. And if we want the B field, then we need to accumulate, right? Accumulate all the little dBs to find the total B field due to all those finite segments. Okay, so let's look at this. ds is the length. It's an S because what if this thing is a curve? So think of it as like the arc length. And I mean, ds could just be straight. R hat is the unit vector. It just is going to eventually make sure that the B field, or the current carrying segment, is perpendicular to where the B field is created, right? And we know that if we do the wrap rule that it's always going to be perpendicular to that. So that's just a unit vector. This usually will just produce a sine or a cosine based on the cross product. R squared is just how far you are away from the little bitty thing creating the current. Okay, so for a circular loop, super easy because ds and r hat are always perpendicular. So when you do ds cross r hat, you just get ds. Also, if you think about all of these little bitty line segments creating this individual B fields, aren't they all the exact same distance away from the point we're interested in, right? We're finding the B field at the center of this loop. So this little r actually becomes capital R. All of these are not functions of ds, so they can all get factored out of the integral. And then if you accumulate ds over that loop, well, that's just the circumference of the circle. And so then the B field is just this times 2 pi r, which is just this. And again, I probably already told you in class that the B field due to a circular loop, meaning a circular wire, the B field at the center is mu naught I over 2r. And now I just proved it using the Biot-Savart law. Okay, well, what if you didn't have a full circle? What if you had a half a circle? Well, it should just be then proportional to how much you've done. So if you think about this is actually in the arc length formula for how much you've done. So if you accumulate ds and you don't go through all the angles, you get this, which is the same thing as saying this, which is really the same thing as saying it's mu naught I over 2r times theta over like 2 pi r, or 2 pi, because you're just taking some fraction of the circle. All parts of the circle create the same B field. So there's a variety of ways to do that, but this should work out. Okay, so this is us proving that the B field due to a circular loop at the center is mu naught I over 2r. Okay, that's the easy one. It's easy because there's no sines and cosines and everything's kind of a constant, so we can pull things out and we don't end up having to do any difficult integral. All right, now I'm going to scroll up to here. Now we're going to do it for a finite wire. And if I had a wire that actually was on, like, let's pretend that was the wire and I wanted the B field at this point A, I would have to do this side separately from this side, right? And so I'm just really doing like one side of the wire, but if I can do one side, then the other side is the same thing. So let's say we have a wire right here, and we're looking for the B field of that finite wire at that point. Okay, so I'm going to use the top angle on this one because I just think it ends up being easier to use this top angle. And I know it's a little weird because it's going to end up being that I'm going to create a cosine rather than a sine because I want the vertical piece. Remember, the cross product always wants perpendicular. The perpendicular piece here, since I'm using this top angle, the perpendicular piece is a cosine. Okay, so I go through all this stuff. Most of you in Calc BC will remember that I am actually doing a trig substitution integral where I'm going to change everything that was r's and dr's. And dx's, I'm going to change them to thetas. This is not something I would put on the test, but the AP could kind of have you kind of set this up. This you certainly write down right away. That's the Biot-Savart law. That is the definition, that B is the accumulation of all the dBs. All the dBs is mu naught I over 4 pi times, in this case I'm going to use x, dx cross r hat over r squared. Okay, so I can write cosine of theta is a over r, tangent of theta is x over a, which means I can get r in terms of theta, x in terms of theta. I can take a differential and get dx in terms of theta. Okay, dx cross r hat just gives you that cosine theta. Okay, so now I can do a whole bunch of substitutions. I can put this in for r. I can put, well, I don't actually have to do anything with this, but I needed that to find dx. So I can put that in for dx, which I did right here, and I get this super easy integral, and the integral of cosine is just sine, and then I can evaluate it from 0 to theta. Okay, so if I want this line to go infinitely far that way, doesn't it make sense that I just keep bending that angle and making it all the way to 90? So if I integrate from 0 all the way to 90, I'm getting half of an infinite line. So if you think about integrating this from 0 all the way to pi over 2, I'm going to end up getting this guy, which is half of an infinite line, because if you double it, you're going to get exactly what we said with ampere, mu naught I over 2 pi a, or in this case 2 pi r. Okay, and again, you're kind of, if I have a line that's goes somewhere to the right and somewhere to the left, I just do two separate integrals, and I really just add that combination. I get mu naught I over 4 pi a, and I get a sine theta 1 plus a sine theta 2. If I make both thetas pi over 2, then I'm making this line infinitely big, and I get a 2 here, and I get exactly what Ampere's law said. Okay, so this trig substitution allows for a super easy integral because it's just so much easier to integrate with respect to the angle. The next page in the notes is the exact same question, except now I'm going to change everything to x's and r's. So I'm going to integrate with respect to a distance. I'm going to integrate from like 0 to L. So same problem, just doing it a little bit different. Here I am going to use the bottom angle, and so I do use a sine theta. Again, I always want the perpendicular piece. So I get a sine theta in this case. Sine theta is x over, or a over r, so I can figure out what r is. R is the Pythagorean theorem, and eventually I still get rid of this sine theta in terms of x. Okay, so instead of sine theta and r, so I have to get rid of this r squared, and I have to get rid of sine theta, and I get them in terms of x. And I get this crazy integral with x's. Now, I can't really normally do that integral, so I use a computer to do the integral, and I end up getting this. So it's going to spit out that integral, and then I evaluate it from 0 to L, and I get this thing. Okay? Now, if you let L go to infinity, then you get this, which is just half of an infinite line. Again, double it to get the equation for our line again. Okay, so as a review, the Biot-Savart law is a given law that we've discovered experimentally, that the B field, due to a really small element carrying current I, is what I've boxed right here. The two cases you kind of have to be able to do are a finite line and then a circular loop or a partial circular loop. Pages 1 and 2 show you how to do the finite line in two different ways, one integrating with respect to the angle, one integrating with respect to x. So one, like you're integrating from like 0 to some angle, and then one you're integrating from 0 to some length. I did the right side on both cases, so if you have a left and a right, well then the B field is the vector sum of those two things, so just add them together. And then the circular loop one really is easy, and again, because there's no sine theta or anything, because these two things are always perpendicular. So take a look at the Biot-Savart law. You should be able to explain how that works. And certainly you can get started. I mean, getting started just means write that down. Okay?